Welcome back. This is the second video of section 3.2 in which I'm going to prove theorem 3.5 that states that the three forms of compactness that we defined are equivalent in the case of a metric space. So I'll do a circular proof. 1 implies 2, 2 implies 3, and 3 implies 1. And the last implication is the hardest one. Okay, 1 implies 2. So consider an infinite subset A of X. So X is assumed to be compact. And suppose by contradiction that A has no limit point in X. So no point of X is a limit point of A. Then we claim that each point in the space has an open neighborhood that I call V sub X that intersects A in at most one point. So it's either empty or just a singleton. The singleton is X in this case. Okay, this is easy. So pick a point X, small x in the big space. We have to distinguish between two cases. If X is not in the closure of A, then by proposition 1.8, there exists an open neighborhood, Vx of X, not meeting A. So the intersection is empty in this case. Now, if X is in A bar, then since X is not a limit point of A by assumption, then it must be an isolated point, because we said that there are two kinds of points in the closure. Limit points and isolated points. So if it's not a limit point, then it's necessarily an isolated point. And this precisely means that there exists a neighborhood Vx that I can take open that intersects A exactly at the point X. So in both cases, the intersection is contained in the singleton X. So this proves the claim. Now we go back to the proof. So indeed, we can write X as the union of all these neighborhoods Vx, X, and X. This is easy because, so how do I prove that? Double inclusion. We encountered such thing earlier. So each Vx is an X, so the union is an X. This is easy. And now, conversely, we take, let us say, an element A in X. Then A is in VA. So A is in the union. So this is really trivial. So the collection Vx, as X varies in capital X, is an open covering of the space. And compactness tells me that X is a finite union of these elements. So in particular, the union contains A. Now, when I intersect, so this means that A intersected with the union is just A by set theory. But A intersected with the union is just the union of the intersection. But A intersected with each Vxi is contained in the singleton Xi, so it could be empty. And therefore, A is just a union of singletons, so it's a finite set. But this is a contradiction because we assume that A is infinite. Okay, so 1 implies 2. And note that this is completely general. We didn't use any kind of metric distance here. So this is true for any topological space. So any compact topological space is limit point compact. Okay, 2 implies 3. So we assume that the space X is limit point compact, and you have to prove that it's sequentially compact. So every sequence has a conversion subsequence. So we pick an arbitrary sequence Xn and X, and we consider the range of Xn. So here we have to distinguish between the sequence as a function from n star into X, and the set or the values taken by the sequence, because a sequence could just take one value if it's constant, or two values, or three values. So the range could be finite and could be infinite. So we have to distinguish between these two cases. Okay, suppose first that E is finite. Then we claim that the sequence Xn contains a constant subsequence, and therefore it's convergent. Okay, so if E is finite, then it contains, let us say, small l elements, A1 through AL. And now, for each n in n star, Xn takes some value, AI. So therefore, we can write n star, this n star, as the union of the set of n for which Xn is equal to AI, because this just means that Xn takes some value. So A1 through AL. Now, since n star is infinite, this means that at least one of these sets is infinite. Okay? So call it, so let's this happen for I equal j. So the set of n for which Xn is equal to ij is infinite. So it's infinite. So what does it mean? It means that Xn takes the value aj for infinitely many indices. And this is equivalent to saying that we can find an increasing sequence of integers n1, n2, etc., and k, such that x and k is equal to aj. Okay, because the set is infinite. How to prove that? Okay, since it's infinite, it's not empty. So pick an element n1 in this set. So x n1 equal to aj. Since the set of n such that xn equal to aj is infinite, when we remove the set of integers from 1 to n1, it's still infinite. So we can find an element in this set. I call it n2, and so on. Okay, so we have now a sequence, a constant subsequence, and this subsequence converge to the point aj. So this proves the claim and the case when E is finite. Now, the more interesting case is when E is infinite. By assumption, E has a limit point x, not necessarily in E, it's in E bar. So in particular, the ball of center x and radius 1, here we really need the concept of ball. Okay, so this is why we assume that we have a metric space. So the ball of center x and radius 1 should meet E at some point. And this point is necessarily of the form x and 1 because E is just the range. So this defines the first term. Next, the ball of center x and radius 1/2 also meets E, but we proved in chapter 1 that actually the intersection is not just different from x, it's infinite, if you remember that. So the intersection is infinite. And therefore, when I remove from this intersection the set of elements xi for I between 1 and n1, okay? So this is a finite set. So when I remove from this infinite set, a finite set, the result should be not empty. So I pick an element in this set. I call it xn2. It's necessarily of the form xn2 because it belongs to E. And n2 now is strictly bigger than n1. Okay, and now you guessed what happens. So then I consider dx of and radius 1/3 and so on. So at the case step, we choose, so suppose that we chose n1 through nk minus 1. This intersection is infinite. Therefore, when I remove from it a finite set, the result is infinite, so in particular not empty. So I pick an element in this intersection. I call it x and k, and nk is necessarily strictly bigger than nk minus 1. So by construction, x and k is in this ball. Okay, so the distance to x is less than 1 over k, and therefore x and k converges to x as k tends to infinity. Okay, so this concludes the proof 2 implies 3. 3 implies 1, the most difficult part. I would divide into 3 steps. Okay, step 1. We prove that, here we assume that x is sequentially compact, and we want to prove that it's compact. So we first prove that the Lebesgue number lemma holds for x. This means that for any covering of x by open sets, there exists a number delta such that so any set of diameter less than delta is contained in exactly one element. Not exactly, but at least one element. So one element is enough. Okay. Now, this is not a circular reasoning because we proved that if x is compact. Okay, so the result would follow from compactness, but we want to show compactness actually. Okay, so we reason by contradiction. Okay, so if you negate the condition of the Lebesgue number lemma, what does it mean in terms of quantifiers? It means that there's no number delta. Okay, so this means that no matter how delta is small, you can always find, so we take delta, for example, equal 1, then 1/2, then 1 over n, and so on. Then you can find a set of diameter less than 1 over n, which is not contained in any element of the covering. Okay, this is just the negation. Okay. So when you take n delta equal 1, then 1/2, then 1/3, etc., as we do as usual, then for each n we construct a subset Cn of diameter less than 1 over n, and it's not covered by one element of A. So it needs more than one element to be covered. So, of course, the n is it's not empty because if it's empty, it's contained in one element. So we can choose for each n an element xn in Cn. And now, so we have now a sequence in the space, and we assume that the space is sequentially compact. So Xn has a convergent subsequence, okay? X and K that converge to some point X. Okay, now, since we have a covering, so the union of element of A in calligraphic A is equal to X, so the small x belongs to some element of the covering, call it capital A. But A is by definition open, because the covering is open. So by definition of openness in metric spaces, we can find a ball of center X and radius R totally contained in A. Now, since the sequence nk diverges to infinity, so for k large enough, we can make 1 over nk bigger than 2 over r. So in particular, 1 over nk is less than r over 2. Okay. Then it's easy to prove that Cnk for this choice of k is contained actually for all k big enough, because it's increasing, the sequence is increasing. So Cnk is contained in the ball of center x and k and radius r over 2. How do I prove that? I take an element, call it x in Cnk, and since x and k is in Cnk, the distance between x and k is less than the diameter of Cnk, which is less than 1 over n, k, which is less than r over 2. So the distance between x and k is less than the radius. So any element here is here. Okay, and since x and k converges to x, then I can make the distance less than any number I like. In particular, I can make it less than r over 2, and this is true for all k large enough. And so by the triangle inequality, the ball of center x and k and radius r over 2 is contained in the ball of center x and radius r. How do I prove that? I take an element here and prove that it's here, so call this element y. So the distance between y and x and k is less than r over 2. And now the distance between y and x is less than the distance between y and x and k plus the distance between x and k and x. So I get r over 2 plus r over 2, so it's less than r. And therefore, any element here is here. And Bxr is by construction contained in A. Okay, so therefore, I proved that Cnk is contained in this ball, which is contained in Bxr, which is contained in A. So Cnk is contained in A. So, and this is a contradiction, because I proved that Cn cannot be contained in one element, but here we have that it's contained in one element. Okay, so this proves that, so my assumption was wrong, and therefore there exists a Lebesgue number delta that satisfies the condition. So this is the first step. Second step, we prove that if X is sequentially compact, then it's also totally bounded. So, right. So pick a positive number, epsilon, and reason by contradiction. So suppose that X cannot be covered by finitely many balls of radius epsilon. What does this mean? So in particular, so we will construct a sequence with no conversion subsequence. So how to choose the sequence? The first point can be arbitrary, so pick a point x1 in capital X. And since bx1 epsilon does not cover x alone, so we can choose an element x2 in X, which is not in this ball. So the distance between x2 and x1 is bigger or equal than epsilon. Okay, and I continue in this way. Suppose that x1, xn are constructed. Now, according to our assumption, the finite collection bx1 epsilon, bxn epsilon cannot cover x, right? So there is an element not in the union. Call this point xn plus 1. So xn plus 1 is outside all these balls. It doesn't belong to the union. So the distance between xn plus 1 and x1 is bigger or equal than epsilon, and so on. So by construction, the distance between an element and between two elements xn and xm is bigger or equal than epsilon, okay, by construction. And this means that no subsequence of xn can converge, because if I had a convergent subsequence, then this would be a Cauchy sequence, and therefore it should be less than epsilon, but it's bigger or equal than epsilon. Okay, so, and this is a contradiction. Therefore, the space is totally bound. Okay, and now finally we prove the implication 3 implies 1. So we pick an open covering, calligraphic A of X, and we want to extract from it a finite subcovering. So by the first step, because the space is sequentially compact, we can find a Lebesgue number delta for this covering and take epsilon to be delta over 3. By the second step, finitely many balls of radius epsilon cover the space. So I call them bx1 epsilon, etc., bxn epsilon. Now, the diameter of each of these balls is at most 2 epsilon, which is 2 delta, which is 2 delta over 3, exactly. So the diameter of bxi epsilon is less than 2 delta over 3, so it's less than delta. Therefore, it's contained in one element that depends on I. So each bxi epsilon is contained in one element, capital AI. Okay. So each of these, so this ball is contained in A1, second ball contained in A2, the nth ball is contained in AN. Therefore, the union is contained in the union of AI, I from 1 to n, but the union is just X. So X is the union of A1 through AN. So the collection A1, capital AN covers X. So we started from an arbitrary open covering and we extracted from it a finite subcovering. And this is just compactness. So this concludes the video and section 3.2. So thank you for your attention and see you next time.